I am happy to introduce the first speaker, Elena Bagryanskaya. She is from Novosibirsk Institute of Organic Chemistry, and the lecture is titled Trityl and Trityl-Nitroxide Biradicals, Structure, Properties, and Application. Please, Elena, you have 25 minutes.
Okay, thank you very much. First of all, I would like to thank organizing committee and especially Matvey Fedin for invitation to present here a talk. It's great enjoyment for me. First of all, it is a possibility to see all my friends and also to look how this field, which I worked maybe 10 years ago or 8 years ago, is proceeding, what is new, and it was really very, very interesting to present here. Secondly, I would like to say some words about Konstantin. Konstantin was really very great scientist, and as Alexandra Yurkovskaya said today, it was rising star. I knew him from student time. Here you see Konstantin, and just because he was a great friend of Matvey Fedin and Timofey Makarov, who were in my group, and we often participate in the same conferences. Also, we were at the same time in Japan and contact a lot. And during the last years, he quite often phoned me as director, and I was really wondering that such a theoretician becomes such a great manager and administrator. So he was very great scientist with a lot of ideas, and I'm very sorry. It was really great loss for all magnetic resonance community. So in my talk, I will speak about trityl radicals. It is overview about trityl radicals, trityl-nitroxide biradicals, structure, properties, and application. I have to say, disappointingly, trityls can't form a crystal with metals. One of students in the group of Viktor Tormashev tried to do it during 1 year or 2 years, and finally he was so much disappointed that he left our institute because nothing was done, and trityl has such a shape and propeller structure that it was not possible, and that was very, very disappointed. Nevertheless, it has a lot of application, and I will briefly talk about all of them. First of all, because time is very short, I would like to say acknowledgement to our chemist. This is group of Viktor Tormashev and Tatiana Troitskaya, Olga Rogozhnikova, and Truhin, who are synthesizers. They are very skilled in synthesis of trityl radicals. Then a group of Igor Kirilluk laboratory, Denis Morozov, Sergei Dobrynin, and Yulia Polyenko. They are synthesizing nitroxide. Larissa Politanskaya and Evgeny Tretyakov were involved in the synthesis of fullerene and trityl compounds. I will shortly say about that. Maria Yedeleva, Dmitry Parkhomenko, group of polymerization, trityl polymerization also. Anna Spitsina, Nargisa Sanbayeva, and Andrei Kuzhelev are spectroscopists who are making all NMR, EPR measurements, and we do a lot of work together with our neighboring institute, Institute of Chemical Biology and Fundamental Medicine, led by Dmitry Pishny, and this is all this Kaverka. And and this work could not be done without Matvey Fedin, Alicia Krumkacheva, and Ivan Timofeev, because they contribute a lot, and many of spectra, which I will show, partly especially pulse, were performed in the Institute of Indian National Tomography Center. So I also would like to mention our collaboration. We heard to the lecture of Takeji Taku and Kazuno Posata, with whom we cooperate. Gerd Budkovsky and Torsten Gutmann, they are measuring DNP for our compounds. Michael Bone is our mega grant leader and spent a lot in our institute during 3 years. Thomas Prisner and Benesh Joseph are doing high field EPR. And Mark Sylvan and Gerard Audrian, we have cooperated for many years, more than 15 years with them. So in my talk, I will speak briefly about structure of trityls, as I show some examples of the application of trityl as spin probes, and then trityls and spin labels and the application to study biomolecules. And it will be one or two examples about trityls application in material science, and trityl and trityl-nitroxide biradicals application in DNP. So what is trimethyl radical, triaryl methyl radical? It has such a structure, and the main peculiarity of this radical is very narrow line in EPR. That means very long electron spin relaxation. Spin density is concentrated on central carbon and is very much closed. And because of that, it has very high stability in many media. So for many years, this radical was used in oximetry to measure oxygen. Why it is? We can make a calibration in model condition, measuring EPR line here at different concentration of oxygen. And knowing this dependence, one can measure EPR tomography and reconstruct concentration of oxygen in the different parts of the sample of small animals. And as a result, for example, this work, I'm not author of this work. This work was done by Artem Gorodetsky in cooperation with Valery Kramtsov. They synthesize such a trityl radical with this phosphonate group. And this trityl is multifunctional. First of all, one can measure oxygen by the line width, one can measure pH because this group is sensitive to pH, and one can measure concentration of phosphate. And concentration of phosphate during the last years, it was admitted that it's played a significant role in the cancer tumor. So, and here you see these images. Also another application, also together with our institute and the Chicago University, it is oxygen guide radiation therapy. In this case, EPR tomography or Overhauser-induced tomography is made, and there are 3 images of the tumor and their concentration of oxygen is made. And then one can use one can make radiation therapy of only the region which has hypoxia, and the result is following that one can use much smaller dose of radiation, and this is very good for health. So I should think I convince you that it is very good for as a spin probe. But we are doing work mainly as applied these trityls as spin label. And in some sense, we were pioneering in the application of these trityl radicals for room temperature. So I have to say some words about pulse dipole APR or PELDOR double electron resonance, or DEAR. It's nice to say that this technique has been proposed by Miller, Salikhov, and Shirov already 40 years ago, and now this technique is widely used among the people who are doing biology and investigating structure of biomolecules. The idea is follow. If we have 2 spins, spin A and spin B, and they are coupled by dipole-dipole interaction, then and we are looking for the intensity of spin echo of observed spin A. Then, if during the time of evolution, we apply additional pulse, which will change pi pulse, we change orientation of spin B, that means the sign of dipole-dipole interaction. And then we are looking for the intensity of the spin echo. As a result, we see something like that. It is decaying oscillations. Then by subtracting baseline and taking this oscillation, one can get, I have no time to explain in detail, but one can get this dipole-dipole interaction. And this, as dipole-dipole interaction is coupled to distance between molecules, one can get information about this distance between two radicals. Then protein is so-called, there is technique so-called side-directed spin labeling technique, when in certain places of protein, different nitroxides are introduced, or trityl, for example. Or if we would like to investigate complexes, we can introduce spin labels to oligonucleotide and nitroxide into the protein, and then we have this information. First of all, if this complexes is formed, and the distance between spins. Making molecular dynamic simulation, one can get structural information about the biomolecule. So we were, like 6 years ago, we were aimed to understand, to try to develop approach to measure the distances at room temperature. Why that was interesting? Because, as I told before, dipole-dipole interaction is the main point. And if we measure this in liquid, then dipole-dipole interaction will be averaged and we can't see anything. So because of that, all these experiments are done in frozen solution at very low temperature. And all this question about how reliable are these distances appear. As a rule, nitroxide I use a spin label, and what we proposed was TAM, the trityl radical. And why that's interesting? Because electron spin relaxation, here you see the dependence of electron spin relaxation with temperature. You see that for trityl radicals, they are much longer. And that was the idea. And another idea was, as I saw before, Viktor Tormashev is very, very skilled in the synthesis of great variety of trityl radical. He can substitute in different position, different compounds, deuterium or other, and by this substitution, one can make radicals either water soluble or hydrophobic or hydrophilic, and also change, for example, if we need some constant here for some project, he can do it. So we, together with a team in ITC, we investigated electron spin relaxation and the mechanism of electron spin relaxation and such things. So we have possibility to choose either to use this Oxter 63, which is non-toxic, water-soluble, or very simply, quite simply synthesized Finland radical. So we have this privilege in our institute. Another point is immobilization. As I said before, we need, if we would like to measure at room temperature, we need to immobilize this molecule. It could be, this can be in water glycerin solution, one can measure only at lower than 800, 200 kelvins, while in room temperature we have to immobilize, and one can immobilize in nucleosyl or some silica gel, oligonucleotide, or in saccharides. In particular, we use trehalose. So, and that was results quite some years ago. In 2014, we performed the first work where at room temperature we measured distance between such a nucleotide, spin label with trityl. This work was really increased a lot of interest, many citation, and many, the main result of this work is validation of the Peldor measurement and frozen solution, because here you see distances at low temperature and high temperatures were the same. That is not always the case. Sometimes it is different, but for oligonucleotide, we got the same result. We also confirm it by NMR because it is quite simple system. And that was validation. And I should say that nowadays, a lot of groups try to perform experiments at room temperature. The idea here is to take very large protein, which rotate much slowly than Larmor frequency, and then one can try to perform experiments at room temperature. We also try, but we failed till now because we have no such a large protein and good biological problem for that. So another point where advantages of trityls is the last work, which has been done by Olesya Promkachova, Ivan Timofeev, and these compounds were synthesized Evgeny Trityakov and Larisa Politanskaya. They synthesized such compounds. For what? The main aim was to show that fullerene can be used as photoinduced spin label. Before it was a paper of De Valentine. She showed she used porphyrines, but here it was fullerene, which has much higher triplet polarization. But I will not talk about this work. I only would like to compare the advantages of trityl. The advantages, first of all, again, electron spin relaxation. So we use here spiral nitroxide, which has very long electron spin relaxation, but TAM is definitely allow one to go to higher temperatures than any nitroxide. And here you see the results. You see here spin echo polarization for nitroxide and for trityl. The first point is that trityl has much narrow lines. That means it can be saturated much better, and while nitroxide have quite wide spectrum. And second, electron spin relaxation. As a result, what we have much higher amplitude of modulation and much better signal to noise. So here we also have this advantage of their trityls. But when this work was performed, the question arises, can we use triaryl methyl radicals for such experiments when we have this photolysis? And Andrei Kuzhelev investigated this question together with Viktor Plusnin, and what they found, if you photolyze triplet trityl, we see that photolysis go on and new products are formed. New products which are hydroquinone, carbon cation, trityl cation, and also this is methyl. This is trityl. Trityl, 3 products, and we investigated by NMR, by mass spectroscopy, just to extract this, to show that they have this, that they are really confirmed by all chemical technique. And the main aim was, if it's possible, to use it. And it was confirmed that quantum yield for Finland radical is very low. That means trityl radical can be successfully used as a spin label for such kind of experiment when the partner is photo-induced spin label. And also, in addition, we investigate this mechanism, and the mechanism of the photolysis is the following. It is photoionization of TAM radical with formation of corresponding carbocation, and then its transfer. We propose that it is such a carbocation, and then it's with atmospheric water, it formed oxygen. And this is very important, that trityl are not very good in reaction with reaction oxygen. And we use this information for future spin labeling of biomolecule. It's much better. In some cases, if we have formation of reaction oxygen species, for example, we have oxygen in some reductant, and then and we have this formation of reaction species oxygen, then the spin labeling have quite low value. So we use it now for spin labeling of the biomolecule using trityl radical. So we understood that trityl can be used as a good spin label. The next work was in cooperation with Thomas Prisna, who used our spin labels and he tried to perform experiments with membrane. That was in cooperation with him, and when they put everywhere nitroxide, they could not see anything because of very wide distribution of spin labeling. But when we make spin labeling of certain places of trityl on the surface and nitroxide inside, then very nice experiments results were obtained. But the problem was that we have here very wide line. That means that Finland radical, our spin label, is not very good for membrane. It forms a lot of complexes without covalent coupling. And as a result, we have very low modulation amplitude here. And that means that one needs to develop new spin label, water soluble, because it was not possible to clean this membrane from this Finland radical. So I asked Viktor Tormyshev to develop new spin labels, water soluble spin label, and he did it. He synthesized such spin label. And the first example is albumin. Olesya Pumkacheva was together with Anna Spitsina performed this experiment. And first of all, and Alexey Chubarov make this spin labeling successfully. And albumin is quite interesting compound, and then several works has been done using this compound. What is interesting? We try to confirm that we develop new water-soluble trityl spin label. Here you see results for oxo-63, which is covalently mixed, yeah, and it is very narrow, and there is no any signal of aggregates. While for Finland, we have very large aggregates, which really are disturbing for experiments. Because so as a result of this work that in former with Finland, many trityls are non-covalently coupled with the albumin, but with oxo-63 everything is fine, and one can measure whatever he wants. And in addition, very nice surprise is that oxo-63 have very long electron spin relaxation, 6.3 microsecond, which is very nice because then it means that one can measure much longer distances than with Finland radical. Last work, not last work, but during this year, a work which was recently published together with Tom Benesh, who now has his own group, we perform experiments with different spin labels. And first of all, what we observed that they are very, very stable in comparison with nitroxide. And in some cases, biologists need really several procedures which are, and the spin label should be very, very stable to perform some experiments. This is one point. And second point is that he observed again for oxo-63 quite long electron spin relaxation with in comparison with other with is results of the investigation of the membrane. You see here quite narrow line for nitroxide and trityl. Here you see the final, so finally we can conclude that trityl spin labels provide longest phase memory time for OXO63, high sensitivity and selectivity for Pell-Dordir experiments and low micromolar range. And this is already in cell. So that was quite interesting thing. So spin labels based on trityl are nice. Another work which was initiated by Thomas Prisner, and what he would like to do, he would like to apply the methodology from NMR for studying multi-quantum counting of different radicals. So that is quite well known in NMR, where they investigate different 2 quantum frequencies, 3 quantum, and so on. Why is this interesting? Because in many cases, aggregates of biomolecule, they formed aggregates, and these aggregates, and then nobody knows which dipole-dipole interaction you're measuring. So one have to know if this aggregate are formed. And in this case, it is model compound. So we would like to know if trityls can help in such cases. Then model compounds like bitrityl, tritrityl, and tetratrityl radicals were synthesized. And you see here that for B radical, we have only 2 quantum coherence, for 3 radical, 2 and 3, and for tetra radical, we have all these 3 lines here. Unfortunately, the technique here is very precise, should be very precise phase and so on. It's really, despite it is X-band, we really can't do it in our place. So this work is continued because we would like to apply this technique for biological objects. And finally, I would like to say some words. I do not know about time, but it's need me 1 or 2 minutes to finish. Trityl-Nitroxide biradicals for DNP. This work has been done in cooperation with Gerd Bunkowski. I suppose it will be continued. We also now cooperate with Songhi-Han. So what is interesting here, you know about DNP, that for DNP, especially which is made in solid state at low temperature, it should be 2 spins, at least nitroxide and trityls. So these biradicals were synthesized. You see that they have different bridges, and I can't say that we got very exciting results, because this the measured by Torsten coefficient of enhancement are not very impressive, but still they are quite large. And what is the most promising, that during last years appear paper where they show that such biradicals have much higher polarization, DNP polarization in high magnetic field, in high frequency NMR spectrometer. So we hope it will be that. So we are introducing to this field with biradical. It's about DNP agent for those who are involved in DNP. I just would like to say about this project with Nargis Asanbayeva. So the idea was that now a lot of interest is for in-cellular DNP also. So for in-cellular DNP, one need very stable radical, both that trityl and nitroxide should be very stable. And the idea was to synthesize biradicals, which are like that, which is extremely stable with trityl, with this tetra-ethyl group, and to use not only TAM, but OXO63, which is water soluble and very stable and very long electron relaxation time, but I am not sure that it's good for DNP. So all these radicals this radical and that one, because here it has quite good group for coupling, but unfortunately this radical is not suitable for us. It has too high reduction rate. So we such biradicals on nitroxide were synthesized, and Trityl-Nitroxide radical were synthesized. And unfortunately, due to pandemic, we could not, and also the problem of DNP setup in Gert lab, Gert Budkovsky lab, we could not measure DNP, but now we have agreement that they will measure during this autumn, or maybe Nargis will come to them and will measure all these compounds for DNP. Maybe DNP. Yeah, I'm finishing. This is the last one. Maybe it will be not very high DNP coefficient, but due to long-lived time, yeah, and very low rate of reduction, they can be suitable for in-cell DNP in future, where inhibition, where it needs quite a lot of time to introduce it into the cell. And this I will not talk about. This is just real methyl polymers. One can also attach trityl to polymer and make it so stable that allow one to make NMP when it's present in the polymerizing solution. So the idea was here to put here trityls, and here it is micelles, and then look into EPR signal. One can get information about disappearance of this. This was already shown in Sato presentation. So I hope I convince you that trityl are perspective as spin probes, as spin labels. Also, it can be introduced to polymers and make trityl polymers and biradicals for DNP. And I'm not sure, maybe you will have some ideas how to use it more. Thank you very much for your attention.
Thank you very much, Elena Grigorьevna, for your nice presentation. I think we have time for one short question, please. Matvey, please.
May I ask a very stupid question? Can you actually, this is concerning photostability of trityl radicals. Can we actually add some troubleshooting groups at the periphery from the radical center, just so that they, absorb light and deactivate it, and then the problem is gone? Can we do it like this, or?
Some group which have been attached to somewhere with superoxide, yeah? I do not know. What we found out that the problem is reaction with superoxide. If it is like alkyl radical, it's very hard to attach to this, yeah? Already high temperature, I showed you that in polymer, where it is a lot of alkyl radical, trityl still is very stable. But with superoxide, it's really formed such a hydroquinone. So I have no idea. I'm not chemist. Maybe Viktor Ivanovich proposed something, or Evgeny Viktorovich, but I'm not sure. It should be something which reacts with superoxide. Concerning other radical, we really look to that. It stay in radical in many cases with other radicals, already radicals. It stay in quite good shape.
Okay. Thank you again, Elena Grigorьevna, for your lecture. Unfortunately, we don't have time, Sergey. Please ask further.
Okay. He just applauded, as I understood.
Let me introduce now the next speaker. It's an honor to present, to introduce David Alan Shultz. He is from North Carolina State University, The lecture is titled Designed Radical-Chromophore Exchange Control, Magnitude of Photoinduced Electron Spin Polarization in Electronic Ground State. Please, Alan, you have 25 minutes.
Thank you, Evgeny. Can you hear me and see
Yes.
my slides?
Yes.
Okay, fantastic. I'd like to first thank my collaborators, Marty Kirk at the University of New Mexico and Art van der Est at Brock University for their collaboration on this project. I'd also like to thank the organizers for the invitation to speak to you here. Although I did not know Kostya Ivanov, it's pretty clear that his colleagues both loved and respected him. So this is a very nice dedication you have given him for this conference. So although I did not know Kostya personally, I do know many people, particularly in Russia, because Victor first invited me to Novosibirsk way back in 2004, and I met Elena and Evgeny and Galina, who's not shown here. And it was my pleasure to also see Paul Ray again, the late Paul Ray. He is missed. And one thing I remember from this conference in Novosibirsk was the fantastic banquet that we had that included music and dancing. And so I will never forget that conference. It was such a great time there. And I met many people from all around the world at that conference. In fact, I had such a great time in Novosibirsk. I went back in 2005, where I was the host of another great chemist, Michael Bubnov, and visited Nizhny Novgorod and the Vesuvius Institute there. And the conference was held aboard this riverboat shown here on the right, where we traveled up the Kama and Volga rivers, making some stops along the way and ending up in Perm. And it was a fantastic time. I have so many fun photographs from my time in Russia. And so I'm very sorry that this meeting was not in person. It's just much more fun to speak and listen to folks in person than it is online talks, but the talks have been very good and the recordings are going to be useful as well. So I'm going to talk to you today mostly about one project that is relatively new, but I have to start with a project that I've been working in collaboration with Marty Kirk on for quite a few years that involve what we call donor acceptor biradicals, shown here on the right, where we have a semiquinone radical attached to any synthetically viable bridge fragment, and then a nitronel nitroxide radical on the left that we call the acceptor radical. By virtue of the structure of these molecules, the bridge can mediate magnetic exchange such that the singlet triplet gap that we observe is comparable to the thermal energy, and we can actually see electronic transitions out of both the triplet and singlet ground states. And so building on a known model that relates that magnetic exchange coupling to the electronic coupling, we can spectroscopically evaluate the excited state singlet triplet gap, and we can evaluate the mean charge transfer energy U, and we can numerically calculate what the electronic coupling is. It can't be determined in a straightforward fashion from other spectroscopic methods for any bridge fragment B. And so we've used that most recently to evaluate any physical measurable quantity that's directly proportional to the electronic coupling matrix element. And I'll show you an example of that in just a minute or two. And so more recently, we're generating these donor acceptor biradicals in excited states by photoinduced electron transfer using these typically platinum or palladium complexes that are square planar D8 metal ion configurations. And the square planarity, and with the assistance of a particular d orbital, there is sort of a pi pathway that connects the catacholate, now donor, with the diimine acceptor. And these complexes all have visible wavelength catacholate to bipyridine charge transfer bands, so that excited state now has a semiquinone bipyradical anion character. But the donor half of the molecule now, if we covalently attach a nitrogen nitroxide radical, has the same charge and spin distribution as the zinc complexes that I mentioned up here above. And so, because of the similarity in the spin distribution here, we understand what the exchange coupling is in the excited state between the semiquinone and the nitrogen nitroxide. And using other spectroscopic techniques, we can spectroscopically measure what the exchange parameter is between the semiquinone and bipyridine radical anions. So we have 3 spin excited states where we have an experimental handle on both of the important dominant exchange pathways. So just to show you very briefly what we're doing with the donor acceptor biradicals, we've counted these molecules as analogs of molecular brake junction devices, where the radicals behave as the electrodes and the molecular bridge fragment mediates the magnetic exchange coupling between the donor acceptor biradicals. And because that exchange coupling is proportional to the square of the electronic coupling, and because the conductance, the electron flow through the bridge is proportional to the electronic coupling, then there's a relationship between the magnetic exchange and the conductance, which we compute. And so most recently, we showed how the computationally determined conductance varies with the experimental magnetic exchange coupling for a variety of different bridge fragments. And we could relate both the conductance and the exchange to molecular orbital and valence bond models that are pretty straightforward for synthetic chemists to understand and should facilitate the design of molecules used for molecular electronics. So these molecules that we use to photochemically generate donor acceptor biradicals in excited states, we're interested in demonstrating manifestations of magnetic exchange in photoinduced excited states. And these chromophores are great platforms for this type of project. And so, as I mentioned, there's a ligand-to-ligand charge transfer in these chromophores. And in fact, computationally, you can observe that the highest occupied molecular orbital is about 90% catechylate donor with a little bit of metal and diimine character, while the LUMO is predominantly a diimine with a little bit of metal catechylate character. And so that ligand-to-ligand charge transfer results in a near unit electron transfer from the catechylate over to the bipyridine and makes these ligand biradical excited states. And so these are a really interesting reversal of roles where you might more typically see 2 transition metal ions linked by a diamagnetic organic or main group ligand, whereas here we have redox-active ligands linked by a diamagnetic transition metal ion. The catecholates here turn out to be key because this singlet excited state, this ligand-ligand charge transfer excited state, despite the presence of the platinum, are short-lived singlet excited states where intersystem crossing is forbidden by symmetry. And so these do not fluoresce, they do not intersystem cross. For all of the derivatives that we've studied, in under 1 nanosecond, they decay non-radiatively back down to the ground state. And as I'll show you, that turns out to be key for our spin polarization studies. When you attach a radical to these chromophores, you now have, as I mentioned in the introduction, a 3-spin excited state. And there are 2 dominant magnetic exchange interactions in this excited state, one between the semiquinone and bipyridine. We've actually measured that with magnetic circular dichroism spectroscopy, and that exchange coupling is 1,400 reciprocal centimeters, while the SQNN exchange coupling is mediated by the bridge, and we use the exchange parameters for our ground state biradical zinc complexes to evaluate that exchange parameter. So in these 3 spin excited states with catechylate donors, we have a quartet and then 2 different kinds of doublets. We have a trip dub where the chromophore semiquinone bipyridine is in a triplet state, antiferromagnetically interacting with the nitrogen nitroxide radical, and the D-sing, where the chromophore is in the singlet excited state, coupled with the nitrogen nitroxide biradical. Because in the absence of a nitrogen nitroxide, the catechylate complexes make singlet excited states that rapidly decay back down to the ground state. By the same token, you do not intersystem cross to quartet states in these radical elaborated chromophores. And so photoexcitation by irradiating the ligand-to-ligand charge transfer band produces the D-sing, the singlet chromophoric doublet excited state that rapidly undergoes internal conversion to D-trip, which now you can observe essentially the triplet configuration of the chromophore, and then D-trip non-radiatively decays back down to the ground state, but in a very interesting way that I'll hopefully quickly go through here. So these 3 spin electronic configurations have been studied for quite a long time. You can read about them in Bencini and Gatteschi's EPR of exchange coupled systems book, and also great chemists Teki and Wasilewski have been studying similar systems as well. It turns out that off-diagonal matrix elements of the exchange mix D-trip and D-sing, and that mixing parameter lambda is a function of the magnetic exchange coupling between the semiquinone and nitrogen nitroxide in this excited state. So since the bridge controls this J, and since we equate this exchange coupling with the corresponding exchange couplings in the zinc complex, we can essentially determine the mixing parameter for D-sing and D-trip by changing the bridge and calculating what lambda would be. So we can essentially synthetically manipulate the energy gaps in this excited state manifold by changing the bridge in these complexes. And so to sort of summarize, we get an excited state where we get ligand-to-ligand charge transfer to make 3 unpaired electrons. We know the 2 major exchange coupling parameters in those excited states, and we can vary the mixing between the 2 doublet excited states by changing the bridge fragment in these molecules. So here are some examples of what the exchange parameters are for these excited states. And so now these exchange parameters come from the zinc complexes that are not shown on this slide, but if there's no bridge and you directly attach the semiquinone and the nitrogen nitroxide, you get strong ferromagnetic exchange of the semiquinone and the NN. A para-phenylene bridge reduces that exchange coupling to about 100 reciprocal centimeters, giving a singlet triplet gap of 200 reciprocal centimeters. Biphenyl takes it down to 220, a thiophene bridge plus 220. No pi system, just using bicyclooctyl takes the coupling down to 1 reciprocal centimeter, and we can even change the sign of the exchange coupling by going from paraphenylene to metaphenylene and make the singlet of the zinc complex the ground state, which reverses D-trip and quartet in the excited state of the platinum complexes. So my students, David Daly and Chris Tichnell, made a series of these complexes where, again, by knowledge of the exchange coupling in the corresponding zinc complexes, we could calculate the D-trip D-sing mixing parameter lambda, which varies as shown here. And then with ultra-fast transient absorption spectroscopy, they measured the lifetimes of the D-trip states of these molecules. And as you can see, they varied when the mixing parameter was relatively large. from 252 picoseconds up to just over 1 nanosecond when the D-Sing D-Trip mixing parameter was quite weak. And so what we demonstrated was control of the excited state lifetime, charge separated excited state lifetime, with exchange coupling, which in turn varies the mixing of D-Sing and D-Trip. And so we can really understand this by the fact that when the mixing between D-Trip and D-Sing is large, then D-Trip has a lot of chromophoric singlet character to it, and the non-radiative decay back down to the doublet ground state is very fast. With longer bridges, or bridges that cause weaker coupling in the excited state, D-Trip has very little D-Sing character, and there's an amount of spin forbiddenness built into the non-radiative decay back down to the ground state. So you get longer excited state lifetimes when you have weak magnetic exchange in the excited state. So that was an example of a rather rare example of a magnetostructural correlation for these types of molecules. The next thing that we wanted to look at, and it was predicted by our MCD studies, was that the excited states would have an amount of spin polarization to them. And after refining the model and doing some experiments, what we realized was we were doing these spin polarization experiments in frozen solutions. And so when you take a solution of these platinum complexes and you freeze them, you're getting a distribution of molecular conformations that can affect particularly the exchange coupling that results in an energy gap between D-Trip and the quartet. And in particular, you're going to get some mole fraction of conformations where there is a very small energy gap between D-Trip and the quartet state. And for spin polarization, this turns out to be key, because if within those conformations with weak exchange coupling, you can set up an equilibrium between D-Trip and the quartet, you can spin polarize the M sub S levels of D-Trip. And under the right circumstances, you can see spin selective decay to the ground state to transfer that spin polarization back down to the ground state. And so we made some complexes, and in particular, we made a complex where we got rid of the diimine ligand that gives us the ligand-to-ligand charge transfer transition. And by doing so, we reveal what many of you already know, is that nitrile nitroxide radicals themselves have an excited state that is nearly coincident with the energies of the ligand-ligand charge transfer excited states. And Marty Kirk's calculations suggest that the quartet that belongs to this doublet transition for the nitrile nitroxide is also very close in energy to that spectroscopically observable doublet. What this means is it's conceivable under the right conditions that there's not only an equilibrium between D-Trip and Q, but an equilibrium between D-Trip and the quartet of the nitrile nitroxide. And both of these equilibria can result in spin polarization by what's called the reversed quartet mechanism that's outlined in this paper at the bottom here. So in the reversed quartet mechanism, you get different signs of time-resolved EPR signals depending on the sign of the chromophore radical exchange. So here, the chromophore radical exchange is the excited state semiquinone nitrile nitroxide exchange. So when that is antiferromagnetic, now the trip dub lies below the trip quartet. And spin selective equilibria between the M sub S levels of those two states results in a non-Boltzmann population of, for example, the trip dub here, that if you were to do EPR, time-resolved EPR on this trip dub, you would see an emissive EPR signal. For us, that trip dub rapidly decays back down to the ground state with a rate constant that's much faster than the longitudinal relaxation rate constant of the nitrile nitroxide. The flip side of the coin is that when the chromophore radical exchange is ferromagnetic, then the trip dub lies above the trip quartet, and you get a non-Boltzmann population of the lower M sub S level of the trip-dub, and that would give rise to an enhanced emissive signal in the time-resolved EPR. Again, for our complexes, the trip-dub is very short-lived, decays non-radiatively to the ground state, and the spin polarization is transferred to the molecular ground state. So Patrick Stewart has now made a couple dozen of these complexes, and in this series that I'll tell you about, we changed the bridge between the catechylate and the nitrogen nitroxide in the ground state, or the same bridge between the semiquinone and the excited state in the nitrogen nitroxide. So no bridge, paraphenylene, dimethyl paraphenylene, where the methyls are ortho to the catechylate, dimethyl paraphenylene, where the methyls are ortho to the nitrogen nitroxide, and then a paraphenylene that has 4 methyl groups on, so that the bridge is nearly orthogonal to the catechylate and the nitrogen nitroxide, which in turn shuts off conjugation between the catechylate and the ground state, or the semiquinone and the excited state, and the nitrogen nitroxide radical. And so I went too fast there. What's happening when we change these bridges is we're changing the energy gap between the quartet and doublet synthetically, but then we're also getting the effect of reduced energy gap by certain conformations that we see by freezing the solution and not allowing the molecules to relax to their equilibrium geometries. So all of the EPR experiments here are done in frozen solvent solutions. So on the left are the integrated continuous wave EPR spectra of these complexes with no light irradiation. And on the right are the time-resolved EPR signals. And so these are effectively a difference spectra before and after the light pulse. So we're only seeing EPR spectroscopy that is a consequence of spin polarization. And so what we see is when there's no molecular bridge, we get a relatively weak time-resolved EPR spectrum. And as we go up through the series and we cut off the interaction between the catechylate donor and the nitrogen nitroxide acceptor, then in the excited state, we generate a relatively greater amount of spin polarization that is transmitted back down to the ground state. Importantly, if we take a look at the complex with DMSOs replacing the diimines, we get no ESP whatsoever. So we need this chromophore radical coupling to generate ESP that gives us enhanced absorptive ESP by the reversed quartet mechanism. And so these experiments were done by Art van der Est at Brock University, who's been a great collaborator. I'd like to point out that while the spin polarization is generated in under a nanosecond, the EPR signal lives for over a millisecond. So there's a very short preparation time for the spin polarization that lasts for, we think, about 1,000 times longer in the spin polarized ground state. So this is we think a nice demonstration of the effect of electron spin polarization that is observed in recovered ground states by photoinduced electron transfer due to exchange modulation caused by both the bridge and frozen solvent solutions. And so I'm not going to read the summary to you because I'm just about out of time, and I have to teach in about, I think about 15 or 20 minutes. So again, thank you to the organizers, and thank you for the opportunity to share with you some of our brand new results.
Thank you very much, David. So colleagues, we have time for question, please. Matvey, please.
Thank you very much. Fantastic talk. Very interesting. I have a very short comment, maybe with question. So I think when you compare liquid solution Jablonski diagram and frozen solution, there is one more difference because these transitions from doublet state to the ground quartet state, they are in fact weakly allowed due to anisotropy of exchange interaction. So in frozen solution, you have this anisotropy. In liquid solution, when your molecule rotates very fast. There is no anisotropy, of course. So maybe this adds some more effects and enhances the efficiency of these transitions. Yeah, maybe not. Just an idea.
So this is a great idea, and if the exchange coupling were due solely to the organic fragments and the platinum plays no role, which we know it does, by the way, then there wouldn't be much anisotropy to the exchange. But we think the platinum does play a role. We have a paper that just came out in JACS that shows that the spin polarization is dramatically reduced when you go to palladium. And so what we would like to do is more low temperature spectroscopic studies and to probe more closely the exchange and the zero field splitting in particular of the platinum biradical complexes. And we're working on that right now, but thank you for that comment. It's spot on.
Victor Ivanovich, please.
I have no question. It was only my reaction. I applauded. Okay. Thank you, David, for your so interesting presentation.
David, I have one question. You use different chromophore in your study. And the question, how are they effective to stabilize excited state? Did you consider introducing fluorine atoms in by pyridine ligand?
So did we include what atoms on the bipyridine?
Fluorine atoms in a position where you have a spin density in this ligand.
Yeah.
So fluorine atom will stabilize both charge and spin.
Yeah. So, another great question. So Patrick Hewitt, my student, has now made a series of these complexes where we've substituted the bipyridine. So doing exactly what you're saying. And we're preparing to send those up to Brock University very shortly. Yeah, okay. Great question.
Thank you. So thank you again, David, for your very nice lecture. And now we will go to the last speaker of this fantastic session, Martin Lemaire. Professor Martin Lemaire is from Brook University. His lecture is titled "Towards Single Component Switchable Conductors Using Redox-Active Ligand Complexes." Please, Martin.
Thank you, Evgeny. Very nice to see you again. Nice to see everyone. Let me just get set up here. So just first of all, just thank the organizing committee for the opportunity to present our work. It's really nice to be part of these meetings. I'll echo Dave's comment about much nicer to have them in person, but given the way things are, obviously, this is what we have to do. And also, I understand the challenging and trying times that you've all faced. And I'll just say that I was very fortunate to have met Kostya at several of these workshops over the years and have just very fond memories that I'll have forever. And his loss is just a terrible tragedy that hopefully time will heal. So just wanted to present our recent work with redox-active ligand complexes towards single component conductors. So just before I get started, I'll share some acknowledgements. We've been very fortunate to have some top-notch collaborators to help us study some of these complicated systems. So the group at OCU, Professor Sato, Takui, and Shugasaki for EPR and DFT, X-ray, Alan and Brian in Canada, and several other collaborators that have been very important for us. All the work's done by these students, and in particular, Nico, who's now graduated, moved on, and is doing a postdoc in Toronto. Funding agencies, of course, NSERC and BROC and CFI. So we are interested in molecular switches, and obviously everybody's familiar with what these are. You have 2 or more states that can be toggled, and generally this involves some sort of external perturbation. So various types of molecular switches. The community that's involved in this meeting is probably most interested in paramagnetic switches that we're familiar with. Several of the talks dealing with spin crossover systems, where you have typically D4 through D7 metals in 6 coordinate complexes that can switch between spin states by changing temperature. That's not the only type of paramagnetic switch. Of course, there's also the valence tautomers. Prototypical example are the cobalt dioxylene complexes that again have also been presented over the course of this conference. And I probably don't really need to go through this with everyone, but the difference between the valence tautomers and the traditional spin crossover complexes is you also have an electron transfer. So you have change of spin state at the metal center, and change and electron transfer from metal to ligand. In this case, you produce the coordinated catacholate and semiquinone with a low spin cobalt-3 as a low temperature isomer. Now, these have been studied for, I guess, over 40 years now. This is the one of the original papers, Pierpont Cannon from 1980, dealing with the prototypical bipyridine cobalt bis semiquinone complex. Of course, you can track valence tautomerism by EPR spectroscopy, where you see a typical kind of radical spectrum at low temperature. And as you warm this up, you get contributions from the cobalt-2 and line broadening and so on. Of course, you can track valence tautomerism, measuring the temperature dependence of the magnetic susceptibility. And if you have systems where there are significant intermolecular interactions, you can have bistability in the magnetic properties. So even though these valence tautomers have been known for several decades, there's still a lot to be learned about them. And there are, I guess, at least 3 current synthetic challenges that I see that in this area. For example, the design of new VT materials where you have a different platform, different redox-active ligand platform. And that recently several have been shown to be involved in this. Also polynuclear VT materials where you have multi-state switching is another very active area. And multifunctional materials where you combine the VT transition with some other property. We're interested in conductivity, so switchable systems that can change their conductivity. So if we look at what's been published in this area, paramagnetic switching systems that also conduct, we see generally what we have are spin crossover systems. So the switching component is an iron complex that has some sort of conducting fragment, typically as an anion. So here we have nickel or palladium demit complexes in fractional oxidation states, provides the conductivity. So you can see those are stacked in crystal structure. And then iron bis Q-sal is the spin crossover unit. So this study was published quite a while ago by Takahashi, and you see the coexistence of spin crossover and electrical conductivity in the same material. And there's several other examples that have been published as well, where you have different conducting units, different spin crossover units, TCNQ, again, in fractional oxidation state as the acceptor. And Dunbar's published recently a similar system, but with cobalt. What we were interested in is, can we produce single component switchable conductors where we have, for example, a coordinated radical directly bound to a metal that's undergoing a change in spin state, where the conductivity is arising from the radical that's directly coordinated to the metal center. So it'd be a single component spin crossover or valence tautomer type conductor. So what kind of redox-active ligand platform do we use? We've been looking at aryl azo ligands. Of course, these are well-known ligands that are, again, redox-active. You can take an aryl azo, reduce it by 1 electron to a radical anion. And again, another reduction produces the hydrazidodianion. Of course, you can track what oxidation state you have for your ligand by looking at the NN bond distance. So the bond gets longer as it's reduced. So what types of ligands that we're interested in are pi extended aryl azo ligands. Here's a typical example. We call this PAPL, and this is an NNO type donor. And there's lots of kind of, I guess, interesting features about these types of ligands in terms of their redox properties. You can modulate the redox behavior by substitution. You can oxidize it to a neutral radical, and you can, again, of course, reduce the ligand to a radical anion. What isn't known, though, with these systems is, can they engage in electron transfer with metals? So that's something that we were interested to look at. And of course, if you could do this, if you could take a metal PAPL complex and have this electron transfer from metal to ligand, could you then have electrical conductivity through stacking interactions and so on in the solid state with the pi radical that's produced in the electron transfer? So, you know, in order to study this, certain things that we need to establish. First of all, can iron and cobalt complexes with aryl azo ligands exhibit spin crossover? Can they also exhibit stable open shell oxidation states in the ligand and valence tautomerism? Can they conduct electricity? And can these two properties coexist in these materials? So can you have spin crossover or valence tautomer conductors with aryl azo ligands? So all of these things weren't really clear. And that's something that we've been engaged in over the last several years. We've made several complexes with PAPL and its derivatives. Of course, if you're looking for spin crossover, you would focus on metals like cobalt or iron. So, for example, first look at some properties of basic metal PAPL complexes. So again, the interesting thing with these complexes is the cathodic redox properties are nice, kind of quasi-reversible. You get reduction of the ligands, and the reduction goes into the alpha beta, and this is a nickel complex. LUMO orbit that was shown here. Now if you make an iron complex, what do you get? Do you get spin crossover? Well, we've made you can take PAPL, coordinate it to almost any source of iron you want, iron 3, iron 2, or iron 0, and you always get the same thing. You get an iron 2 complex neutral, okay, with 2 coordinated PAPL anions. And in this case, you see from the Mossbauer spectra over different temperatures that this is completely low spin, diamagnetic. There is no spin crossover in the system. Now, what about other metals? Well, what about cobalt? So if you take PAPL, coordinate it to, this is dicobalt octocarbonyl, you can generate cobalt-2 complex, again, PAPL anion. And in this case, we do see a spin crossover, and we can track that using magnetic stability measurements, and also by X-ray, two different temperatures, you can see the differences in the coordinate bond distances. The longer bond distances typically in the high temperature form, and you see the Jahn-Teller axis in the low spin cobalt-2 state. So we have established that we can see spin crossover in the system with these aryl azo ligands. What about valence atomerism? Well, another ligand that we have produced is similar to PAPL, but we have a quinoline ring instead of pyridine ring. We call it QAPL. Again, if you coordinate this to, again, it doesn't matter what kind of iron you use, what oxidation state, you always get the same thing, a neutral complex with two coordinated QAPL ligands. And here's the crystal structure. Again, it looks like it's an iron 2 with two coordinated QAPL anions, but this system is quite unusual. And not only in the solid state, but also in solution. So in solution, we see, there's another view of the crystal structure, just kind of rotated around. In solution, in the NMR spectrum, we see two sets of signals. And there's a temperature dependence, kind of suggests that we have two diamagnetic species in equilibrium with one another. So one set of signals decreases in intensity and another one increases as we change temperature. And so what could possibly be going on here? Well, if we look at the UV visible spectrum, we compare the QAPL complex to the iron PAPL complex, we see roughly similar features, except in the QAPL complex, we have this very low energy shoulder, and we deliberately made an iron 3 complex by oxidation of this iron QAPL complex. And if you compare the UV visible spectra of the iron QAPL parent complex and then the oxidized complex, we see this feature in the oxidized complex as well. In the iron QAPL complex that's not oxidized, there's a temperature dependence. And so what we think we have, again, this is a work in progress, but what we think we have here is in the green spectrum, which has this temperature dependence, the iron QAPL complex that's not oxidized, we have electron transfer. So we have valence atomerism without a change in spin state of the metal. So we're going from iron 2 to iron 3, and a QAPL anion to a QAPL dianion radical. Now, in both cases, both complexes would be diamagnetic. So we have low spin iron 2 and two anions coordinated, or low spin iron 3 with one radical, where we would have strong antiferromagnetic coupling, resulting in diamagnetic system, which we see reflected in the proton NMR behavior in solution. We also see in the solid state two iron sites in the Mossbauer spectra, which again have Mossbauer parameters that suggest two different oxidation states of the metal. So what our working hypothesis here is that we have valence atomerism with this QAPL ligand, as I mentioned, low spin iron 2, QAPL anion going to low spin iron 3 with one anion and one dianion radical. But this is still something that we are studying, trying to iron out the details of the system. Now, a more clear example of valence atomerism in aryl azo complexes we've recently published in ChemCom is with this ditopic aryl azo ligand. So we've produced this. I won't go through the synthetic details, but it's only a couple of steps to make this. And if you coordinate this ligand to metal perchlorates, you get these very kind of strictly grid 2x2 grid type complexes. We've made iron, nickel, and cobalt versions of this complex, and in all cases, these are neutral complexes, no counter anions. Now, for the nickel and iron complexes, we see very typical metal aryl azo type behavior. So you have very intense visible absorption bands, suggesting that we have a coordinated ligand dianion just by simple deprotonation of those two phenols. But with the cobalt complex, there's something completely different. The cobalt complex, we have this very, very low energy band in the near IR and a very different electronic structure. In fact, if we take the nickel complex, which is this green spectrum, and we reduce it with some reducing agent like sodium metal or something, we see a band grow in the same region that we see with the cobalt complex. So that band is associated with the reduced form of the ligand, which is a trianion radical. So this is the form of the ligand that we have in the cobalt complex that we produce simply by reacting the ligand with cobalt perchlorate. So we have a coordinated trianion radical, and cobalt is in the +3 oxidation state. So this is confirmed by the X-ray result. You look at the coordinate bond distances, they're very, very short, indicative of cobalt-3. The ligand bond distances are again unusual. We have one long NN bond, one shorter NN bond, again consistent with this sort of valence bond representation of the ligand. Now, again, the group at OCU has carried out lots of important experiments here on this system, and some DFT calculations have again confirmed that the ligand bears all the spin density in this complex. So we have diamagnetic, low spin, of course, cobalt-3 with ligand trianion radical. Now, we carried out some powder EPR spectroscopy on this system. At low temperature, we see a typical kind of radical type spectrum that as we increase temperature changes, the lines broaden, G factor changes, all consistent with electron transfer. So as we increase temperature, what's happening is the ligand is reducing the metal. Okay, we have electron transfer from ligand to metal. In other words, valence atomerism, and we even see that of course, in the magnetic data. So this is the SQUID data. Again, low temperatures consistent with 4 coordinated radicals. At high temperature, we have a higher value of chi-t, which is consistent with this equilibrium, where we have 1 cobalt 2+ and 1 ligand dianion. So in this complex, we have a single electron transfer. So there's only 1 electron transferring from ligand to metal. Clearly have a valence atomerism occurring in the system. Now, we've measured the conductivity of this complex single crystals, and there is no conductivity. It's an insulator. So we haven't established any conductivity with this system, but incidentally, I know lots of people are interested in lanthanide coordination chemistry of these types of ligands, and we've made several lanthanide complexes of this ligand that have this same type of pentanuclear form. So we're still working on this. Hopefully, in later meetings, I can talk to you about these systems. Now, the next thing I want to talk about is electrical conductivity. So we have looked at this new ligand, PHPL. This ligand has a 9,10 phenylalanine substituent. You can make this in 2 steps. It's a tridentate ligand, and it has an interesting kind of redox series that's typical or similar to dioxylines, where we have, when you doubly deprotonated a anion form, you can oxidize it to by 1 electron to an anion radical form. Another oxidation gives you neutral kind of quinone type aryl azo ligand. Now, this ligand PHPL, you've coordinated to several metals. Let's talk about the iron complex. So if you start with iron 2 or iron 3, you get the same thing. It's a neutral complex with iron and 2 coordinated ligands. And this is the crystal structure. It's unclear what the oxidation state of the ligand is, but if you look at if you rotate the structure around, you can see that the ligand is kind of in 2 forms. One is planar, one is kind of floppy. And what we actually have are 2 very different ligands. So one ligand is in the dianion form, the other one is in the anion radical form, and we have iron in the +3 oxidation state. So we have a ligand mixed valence system in this complex. Now, if we look at the IR spectrum. You see this very, very intense and broad feature centered at around 3,200 wave numbers. Now, we've calculated the electronic structure of this system, and this happens to be an IVCT band. So an intervalence charge transfer transition from the ligand dianion to the ligand anion radical. And in this system, we have low spin iron 3+, and the complex is completely diamagnetic. So there is no spin transition or anything of the sort, low spin iron 3+. However, what's interesting about this complex is that it is a conductor. So we've measured the single crystal conductivity of this complex. Has actually for a discrete molecule has actually relatively high conductivity at room temperature, a semiconductor, and has an activation energy of 245 millielectron volts. So we're currently trying to work out the mechanism behind the conduction. It's not clear, and so we're looking at some band structure calculations currently with this system. So we've established now that we can have conductivity in these systems. We've established that we can have spin crossover and valence atomerism. Now, can we put them all together in a single component material, which is ultimately what we're after? So one of the problems we have is that with many of these systems, the ligand field is too strong. And so we have low spin states, the metal, with no spin crossover properties. So what we've been attempting to do is make heteroleptic complexes where we use this shift-based ligand Q cell, and iron Q cell complexes are well known. And we can make this precursor complex that has one Q cell, one iron, and two chlorides, and then make heteroleptic systems with our aryl azo ligand. So if we react this precursor with QAPL, we can make the heteroleptic complex as a tetraphenyl borate salt, one Q cell, one QAPL. And we've made several derivatives of this. We've used halogenated Q cells and so on. Now in these complexes, we can actually generate spin transitions in solution, shown here. This is some EPR data at low and high temperature, UV visible, and some Evans method magnetic studies that have shown that the existence of spin crossover in these systems in solution. We do see spin crossover in the solid state, but it's not very spectacular. We see very, very kind of gradual spin state changes at between 300 and 400 Kelvin. However, we have made a similar complex recently with the PHPL ligand. So we've taken the iron Q cell precursor, coordinated to PHPL, and have made this complex as a chloride salt. So we have iron Q cell with a coordinated PHPL. Iron is in the +3 oxidation state, and the PHPL ligand, remember, can exist in several different oxidation states, is coordinated as an anion radical. So in this complex, we see the coexistence of spin crossover. So this is the chi-T data versus temperature for this complex, and conductivity. So this is actually this plot is resistivity versus temperature, but this material is also a semiconductor, and both properties are in the same complex. So this is an example of a single component spin crossover conductor. I don't know of any other ones that have been reported. So we've proved that we can do it. We just need to make enhance the properties. So that's what we're engaged in now. We've established that we can make these systems that exhibit spin crossover or valence atomerism and conduct. We've established the coexistence of spin crossover and electrical conductivity in these aryl azo complexes. And what we're working on now is trying to enhance those properties and make them better. See if we can generate valence tautomeric conductors, and also moving into looking at SMM conductors using the PHPL ligand, because almost everything that we make with it conducts electricity. So it's a very unusual ligand system. And with that, I will conclude my talk. Again, thank you for your attention.
Thank you very much, Martin. Who would like to ask a question, colleagues? Fabrice, please.
Yes, thank you. Hello, Martin. I hope everything is fine in Canada.
How are you?
I'm fine, thanks. I have a question regarding your system in which you have coexistence between iron 2 and iron 3. I think it was around about slide 13 or something like that.
Okay.
Because I'm quite surprised that the exchange interaction is so strong in case of your iron 3 and the radical. So you say that probably the two states are diamagnetic regarding the NMR, right? But in some time you can have a quite sharp peak in NMR, even if your compound is paramagnetic. So my question is, have you checked your, let's say, diamagnetic states by magnetic measurement or EPR or something like that?
Yes, that's a very good question. We've looked at the solid state magnetic properties and EPR in solution and in the solid state, and we get nothing. So the material appears to be completely diamagnetic.
Okay, thank you.
Victor Ivanovich, please.
Thank you, Evgeny. Thank you, Martin, for your presentation. Can you show your slide number 15, for example? Okay, yes, it's okay, it's okay. Maybe it's fantasy. As I understood, you develop principally approach that allows everybody who would like to insert instead pyrimidine any another organic fragment. Yes.
Sorry, I didn't catch the last part.
In the center, instead pyrimidine, it's possible to introduce any other fragment.
Oh, instead of pyrimidine.
Yes.
Yeah, I mean, we've looked at substituted pyrimidines. I mean, we haven't changed the heterocycle, but there are lots of
it's my idea is so principally, you know, just before your presentation, David presented his don't accept approach, and after excitation, he period for any time before relaxation, this corresponding bridge, this multi-spin state. In fact, your system is absolutely stable. But if you principally you introduce instead pyrimidine something like bridge in David manner, it's possible to create, it seems me, it's possible to create multifunctional material that have reaction not only like temperature-induced spin transition, but at the same time will be able to accept radiation. So it will be additional possibility to play this very sophisticated system of spins.
Yeah, no, that's a very good point.
It seems it's possible, but principally it's possible.
I think so.
Yes, thank you. It's a very interesting idea.
Thank you. Yeah, thank you very much.
Martin, I also have a question related with this pyrimidine-containing ligand. You successfully prepared complexes with nickel and cobalt. What about mixed metal complexes containing both cobalt and nickel? Is it possible?
We've been trying with lanthanides and cobalt, as well as cobalt and iron. We think we have some mixed systems, but it's been very difficult to solve the crystal structures. We can get crystals, but they're tremendously difficult to refine, and that's where we're stuck right now. But we do have mixed systems, definitely. That's a good point. We're just having trouble getting the structures solved.
Okay, thank you. Colleagues, please join me and let's thank all speakers of this session. So thank everybody. Maybe now organizers want to say something.
Yeah, we are actually late anyway. So I suggest that we go straight to the poster session and maybe have some rest during talks with presenters. So please, let's continue with the poster session for the next 40 minutes.